Okie dokie, chemists, let's get started. A quick announcement. I gave everybody credit for one question in Chapter 17 homework. So that 1 point automatically went to the grade book because online homework grades are live. So as you complete questions, even partially, they'll go into the grade book and accumulate over time until that due date. And then penalties will start to be applied to subsequent questions. So since I gave everybody credit for that one question, a lot of folks have 1 out of 60 now on the Chapter 17 homework. Don't worry, that's not affecting your final letter grade. You still have time to accumulate those points. So you don't need to complain about free points. All right, there was an issue with one of the rounding of the questions. Pearson was bad, and they rounded in intermediate steps. You're not supposed to do that. And so their answer rounded in intermediate steps. So if you didn't do that, it wouldn't accept the answer. So I gave everyone credit for that one question, so you don't have to worry about it when you go to do online homework. All right, so let's get back into buffers and talking about the Henderson-Hasselbalch equation. So in Chapter 16, we calculated the pHs of solutions that just had the acid, the weak acid. It just had the weak base. So we would just do x squared over initial concentration to calculate pH using the respective Ka or Kb. But with buffers, it's a little bit different because in this case, we actually have large amounts of both the acid and its conjugate base, or a base and its conjugate acid. And so we make an approximation here. It's still an ICE table, but we make an approximation where we get rid of the minus and plus x in both the numerator and denominator. And so once you make that approximation, and take the negative log of both sides, you get the Henderson-Hasselbalch equation, which we just use when we have a buffer system, meaning we have large amounts of the conjugate base and the acid, or the acid and its conjugate base. And so we see the pH is equal to the negative log, so pKa is equal to negative log of the Ka value for that system over plus log base over acid. Since both of these things are in the same volume, you can also just take the mole amounts that are present in each, and you'll still get that same base to acid ratio. So let's jump back into it and utilize the Henderson-Hasselbalch equation. So we did one where I told you the mole amounts of each, the acid and the conjugate base, to form the buffer. So a lot of this is identifying what is the acid and what is the conjugate base, so you do this ratio correctly. And so we see that this first one, we can take these mole amounts. We don't even have to divide both of them by 1 liter. It's not necessary. Here in this fraction, you see that it's 0.5 molarity of HF over 0.15 molarity of NaF, but we could have easily just put 0.5 moles of NaF over 0.15 moles of, what is that, HF, and we would have gotten the same answer. Again, trying to show you tricks to speed up calculations on exams, and then you plug that in and then you're good to go. All right, so let's do another one. This one's a little bit different. Here we're making a buffer by mixing two things, 25 milliliters of 1 molar HF and 12 milliliters of 1 molar NaF. So we're still going to use the Henderson-Hasselbalch equation, but we need to get that base to acid ratio. So here are my tricks where they will become important. So we need to get mole amounts of each, the acid and the base. Right now I just have milliliter amounts of a certain concentration. So we can get the mole amount by multiplying the volume by the molarity. And here's the trick. There's no need to convert this into liters. We don't need to convert 25 milliliters to liters. I know we would have done that in 1210, but if we take a milliliter and multiply it by a molarity. So 25 times 1 is 25. This is 25 millimoles of HF. Just multiply them straight. Do the same thing to NaF, again, keeping it in milliliters. How many millimoles of NaF is present? Easy numbers, 12. Yes, 12 millimoles of NaF. And so these numbers, 12 and 25, they're a lot nicer to work with than 0.015 and 0.012. Those are a lot smaller numbers. So if we just leave it in millimoles, we'll still get the same answer as long as we divide a millimole by a millimole. So we use the Henderson-Hasselbalch equation now. So pH equals pKa plus log base over acid, and so we have the pKa from, it's the same system, so pKa is still 3.18 plus log, what number goes on top? 12 or 25? So the base needs to go on top, so which one? 12 or 25? 12, thank you, yes, 12, because that is the base, so 12 millimoles of NaF over 25 millimoles of HF. So see how this mole ratio still, it saves us a step of converting both of those into molarity. Again, since they're in the same volume, we don't need to divide by volume for both of those to get to molarity for our answer. And so yeah, you put that in your calculator and you get this one's a little bit more acidic. It has a pH of 2.86. Right, and so that is the strategy there. Identify how many millimoles of each, the base and acid you have, plug it into Henderson-Hasselbalch with the respective pKa. All right, let's do another one. This one's a little bit different because the system now is with ammonia. So let's calculate the buffer. That is a solution of 0.15 molarity ammonia and 0.12 molarity ammonium chloride. So here I just straight give you concentrations, so these will go into our base to acid ratio. So ammonia will be what? The base or the acid? It's going to be the base, yep, because ammonia is a base, and then ammonium chloride is going to be the acid by process of elimination. So we have those, both those terms, the log base to acid ratio. Now we just need to get the pKa, all right? So I give you the Kb for ammonia. So if I take the negative log of this number, is this number going to be pKa? Nope, it's going to be pKb. But let's go ahead and calculate that. So here, if you negative log that number, you get pKb equals 4.74. All right, so to get pKa, we have to use the Ka value. There's a couple ways you can do this. You can say, okay, Ka equals Kw over Kb. We know what Kw is. Again, assume this is at 25 degrees Celsius, and you can get a number. I actually didn't write this down. Okay, 1e negative 14 divided by 1.8 E negative 5. So the pKa for ammonium is 5.55 times 10 to the negative 10. So if you negative log that number, so let's do that, negative log, where's log on this thing? That number, you get 9.26. Okay, is there anything special about pKa and pKb? They add up to 14, yeah, so there's two ways that you can convert between pKa and pKb quite easily. Of course, you can always use Kw like we did in chapter 16, but if you have a pKa, you can easily get a pKb, vice versa if you recognize that they have to both add up to 14. All right, so we're going to use this pKa value in our Henderson-Hasselbalch equation. The way that we calculate pH, it always uses the pKa value. So even if it's a base system, you have to convert to pKa. So pH equals 9.26 plus log base, which we identified as ammonia, so 0.15 molarity ammonia, that is the base, over 0.12 molarity ammonium, which is the acid. And of course, this is in the form of ammonium chloride, but chloride is a pH neutral salt, so we can essentially just ignore it. That is the concentration of our conjugate acid ammonia. And then you get that answer is 9.35. So this buffer is in the basic region because it is made with a weak base system that has a pKa that's in the basic regime versus the HF system we used, its pKa was in the acidic regime. All right, let's do another one. where we calculate the pH of a solution, but this time we're mixing two things. So 200 milliliters of ammonia and then 800 milliliters of ammonium, right? So those are our two systems. We can't just put in those molarities straight up. We have to actually calculate how many moles of each of them we put into this buffer solution. We want to know what is that base to acid ratio. So we can't just simply put 0.4 over 0.1. We actually have to calculate the millimole amounts. So multiply these two numbers together. 200 times 0.4. What is that? What is that? This is, I think, what, 800? Or no, 80. 80 millimoles of ammonia is what we put into that solution. And again, no, you don't have to convert to liters. We can just stay in millimoles. And 800 times 0.1, that is 80 millimoles of ammonium. So there we go. All right, and so those are the two millimole amounts. That is what's going to be my base to acid ratio in this example. So pH equals that same pKa as before, so 9.26 plus log over base over acid. So this is 80 over 80. So this is millimoles of ammonia and millimoles of ammonium. All right, and so this highlights the importance. So we got a ratio where the base to acid ratio is 1. The amount of acid and conjugate base that are present is 1 to 1, but we added different volumes of each of them with different concentrations. So that highlights the importance of calculating millimoles for this base to acid ratio versus in the previous example, I just gave you straight concentrations with no volumes. It's assumed that both of these are the same in the same solution in the same volume, so we can put those values in straight up. But in this second one, we actually have to calculate it. All right. Hopefully, without putting anything in your calculator, what is the log of 1? Or just put it in your calculator so you can check. What is it? It is 0, yes. So log of 1 equals 0. So we see that our pH is 9.26. So this is kind of something special. When your base concentration is equal to your acid concentration, your pH is going to be equal to your pKa, and the reason is because you're taking a log of 1, which is 0, and so you can make a buffer system with equal amounts of your acid and base, and that pH will be your pKa value that's tied to the identity of your buffer system. So in this case, it's ammonia and ammonium, so we're able to get a pH equals pKa for that system. All right, okay, so that is for a base system. Let's do some more of them. All right, but I ask it a little bit different. Okay, so yeah, we can figure out how much base we have, how much acid we have, so let's kind of go about those variables a little bit differently now. All right, so this time I tell you we have a buffer with this certain pH, and it's made with acetic acid. What is the base to acid ratio? So if we look at the Henderson-Hasselbalch equation, I give you pH, we can calculate pKa, and so the variable we are solving for is in that log. We're figuring out what is that base to acid ratio. That is what we're solving for this time. In all the previous ones, we calculated base to acid ratio to get pH. Now we're just kind of working backwards. So we do need to get the pKa, so take the negative log of that Ka value. You're going to be working with acetic acid so much, I bet by midterm 3 you will memorize that the pKa of acetic acid is 4.74. You're going to use it so many times, you're just going to know that it's 4.74. I promise. All right, and so that is going into our Henderson-Hasselbalch equation. So 4.70 equals 4.74 plus log base over acid. So we're solving for that whole ratio inside the logarithm. But before we solve it, what do you think is more present based upon our measured pH versus the pKa that is given for the substance? Is more base present or is more acid present, you think? Acid, yeah, because the pH, the measured pH, is a little bit more acidic than the pKa, so probably a little bit more acid is going to be present. And so we can just kind of, guesstimate that given the numbers that we have. So solving for this, we want to isolate that log. So I'm going to subtract both sides by 4.74. So I get negative 0.04 equals log base over acid. So how do I undo a logarithm? Take 10 to the caret of both sides, all right? So 10 to the negative 0.04 is equal to, did I write this down? 0.912. And so that is what the base to acid ratio is, all right, 0.912. So yes, that's the ratio. So let's remind ourselves kind of how we can use this ratio. So I like to put that number we just calculated over 1. So 0.912 over 1. And so what this means is for every 1 unit of acid we have to have 0.912 units of the base present. And so we were right, there's a little bit more acid versus the base that's present. So that's what that ratio means, right? For every 1 acid, there's 0.9 units of that base. Okay, so we got the base to acid ratio, so how can we use this? So let's see, how many moles of acetic acid should be added to some amount of sodium acetate to make this buffer? So this is just dimensional analysis. Look, we have this ratio that works as a conversion factor. I know how many moles of sodium acetate I have. So sodium acetate is which component of the buffer? Is it the, oh my gosh, is my pen dead? So sodium acetate is which component of the buffer, the acid or the base? Sodium acetate. Not all at once. It is the base, yes. So I'm giving you how much base we have, right? So if we multiply those numbers together, I'm not smart enough to do it on my own. Okay, there is 250 millimoles of the base present. And so we can use that number plus the ratio that we just got, all right, so 0.25 millimoles of base. We'll use the ratio now, but where am I going to put that 0.912? Am I going to put it on the top or the bottom? What do we think? Not on the top. So right now I'm in the unit of base, so I want to put the base number on the bottom. So I'm actually going to put the 0.912, we can say, okay, for millimoles of base is required for every 1 millimole of acid that I need in my buffer to make this certain pH. And so we get like 274 millimoles of acid is required, and so this question asks for moles, so now we can convert this into a mole amount, so divide that by 1,000, and we get that we need to add about 1/4 of a mole of acid, so acetic acid, to this solution to make the buffer have the correct base to acid ratio to produce a pH of 4.7. All right, so in the first part of this question, we calculated the base to acid ratio, used that ratio, understood that that ratio is base for every 1 unit of acid, canceled out units just like in 1210 with dimensional analysis. See, the bases cancel. We're left with acid up top, and then we get how many moles of acid we need to generate this specific buffer. All right, so there's another buffer question. Are we going to do another one? No, okay. So in all of the previous examples, I gave you how much acid and how much base were present in the buffer. I gave you straight up like acetic acid, sodium acetate, ammonia, and ammonium, all right? So I gave you values for that base to acid ratio directly. So where things can get complicated is there's actually multiple ways you can make a buffer. There's 2 ways. There's 2 ways you can make a buffer. And so this slide just kind of summarizes those different ways. We actually just did this first way. The first way to make a buffer is you add HA and A- directly. In all of those examples, we calculated how many moles of acid, how many moles of the conjugate base we had from the information given. Or it can be base and conjugate acid, whatever. But there's another way we can make a buffer, because the idea is all we need is an acid and its conjugate base present in that solution. The second way we can make a buffer is via partial neutralization. If we start with all weak base, so HA, and we add a strong base like sodium hydroxide, we neutralize it. All right, so this is what we're going to move on next is down here, the second way to make a buffer via neutralization. So take a weak acid like HF, you add sodium hydroxide, just a little bit of it, so a partial neutralization. And when these things become neutralized, if you remember 1210, do that double displacement, look and see what's produced at the end. Right? When you partially neutralize HF, you make NaF in that solution. And so if you partially neutralize this, by the partial neutralization, you will have both NaF and HF present in your solution to have that buffer. All right, so this is via partial neutralization. You convert some of the moles of HF to something else, that conjugate base NaF, and that's how you get your base to acid ratio. So in this first one, we just calculated moles of each. That's the base to acid ratio. This second one's a little bit harder because we actually have to do a BCA table first before we do the Henderson-Hasselbalch equation. I'll show you examples on how to do that, because what you're adding to your beaker is actually acid and strong base, so you need to figure out how much strong base you add to convert to that conjugate base to then put into your Henderson-Hasselbalch equation. So you have to BCA table first, then you need to do the Henderson-Hasselbalch. So I will show you examples here. All right, so this one is, okay, this is the second type of buffer. We have HA and we mix it with a strong acid. Strong base, right? So let's see what we're putting in our beaker. We are putting 80 milliliters of HF and 15 milliliters of sodium hydroxide. So obviously HF is the acid. Don't think right off the bat that sodium hydroxide is the base. Because remember, when we do the base to acid ratio, right, log base to acid, we need the conjugate base and the acid. So sodium hydroxide, this value doesn't automatically go into that base spot in our log ratio here. We need to figure out actually how much F minus and how much HA we have in the solution once we mix these two things together. And that's what the BCA table is for. But let's just get millimole amounts first, because we have to use that in our BCA table. So I think I can do this in my head. 80 milliliters times 0.1 molarity HF. How much millimoles is that? 8. So 8 millimoles of HF. And I am mixing how many millimoles of sodium hydroxide? Is that 3? I don't know. 15 times 0.2. Yes, it is 3. So I'm mixing 8 millimoles of HF and 3 millimoles of sodium hydroxide. So our base to acid ratio is not 3/8, because this is 3 millimoles of sodium hydroxide. I need to figure out how much F minus, the conjugate base, I have. So this is where the BCA table comes into play, all right, where these millimole amounts go into the before line. So I have 8 millimoles of HF. I have 3 millimoles of sodium hydroxide, and I have 0 of that stuff, right? Remember, BCA tables, we're not predicting the direction or anything. We want to consume the limiting reactant, and then that dictates our change line. So based upon these numbers, which substance is our limiting reactant, HF or sodium hydroxide? Sodium hydroxide. So our change line, I'm going to consume all of that sodium hydroxide so it is fully consumed. So if I consume 3 millimoles of the strong base, sodium hydroxide, how much HF do I also have to consume? 3. So minus 3. Then In that process, if I consume 3 and 3 of HF and sodium hydroxide, how much sodium fluoride do I make, the conjugate base? 3. So it's plus 3. And then I also make 3 millimoles of water, but it doesn't really matter. And then we add up our columns. So after this partial neutralization, I have 5 millimoles of HF, and I have 3 millimoles of NaF, and then I have 3 millimoles of water, but that's not going to affect our pH. All right, so what is our base to acid ratio for our Henderson-Hasselbalch equation? It's not 3/8, it's actually 3/5. So this after line, after this partial neutralization, this is the base to acid ratio that we put into the Henderson-Hasselbalch equation. We can put so remember the Henderson-Hasselbalch equation is an ICE table with the approximations already done for you. So after this partial neutralization, you have HF and F- in solution at the same time. That's a buffer. So we can stick these numbers into that Henderson-Hasselbalch equation. So pH equals pKa plus log base over acid, right? Oops, we didn't get the pKa yet, so here's the Ka for HF. So pKa equals, I think I got it before. Is it 3.18? All right, so our pH for this buffer is 3.18 plus log 3 millimoles of F- over 5 millimoles of HF. And then, whoops, there you get that pH, is 2.96, right? So there's a little bit more acid present, so our pH is a little less than, a little bit more acidic than that pKa value, right? So this buffer question via partial neutralization is a little bit harder because you have to do a BCA table first to figure out, okay, how much of my acid is neutralized before you put it into the Henderson-Hasselbalch equation. But I'll point out, once you do a lot of these, there's you'll see that there's a pattern, and you don't actually really need to do a BCA table as long as you really understand what reaction is happening. Because in this neutralization reaction, everything's a 1-to-1 ratio. And so it's very predictable once you do a lot of them. All right, let's do another one. But this time it's with a base. So let's start with a weak base, and now let's add a strong acid. All right, so let's calculate the pH when we mix ammonia and HCl. So here's the Kb. We got the pKb of ammonia before. It's 4.74, or sorry, that's Kb. So that means the pKa, pKb is that. So the pKa for ammonia is 9.26. So that's the number that we're going to have to use later. All right. So the strategy here is recognize you're adding a weak base and a strong acid and partially neutralizing it. So let's get those millimole amounts. Oh, look, they're the same numbers. 8 millimoles of ammonia, so that's the base, so NH3. And then we have, what is this, 3 millimoles of HCl, which is a strong acid. Weak bases are neutralized by strong acids, so we're going to partially neutralize this first using a BCA table. So we see that ammonia, we start with 8 millimoles of ammonia, 3 millimoles of HCl. We have 0 of the other stuff. Okay, so the numbers are the exact same. What is our limiting reactant this time? HCl. So we see we consume 3 millimoles of HCl, but then we also consume 3 millimoles of ammonia. So then we gain 3 millimoles of ammonium, the conjugate acid, and then 3 millimoles of water, but again, we'll ignore that when we do the Henderson-Hasselbalch equation. So we add up all of those columns, and we see after this partial neutralization, I have 5 millimoles of ammonia present. I have 0 HCl, but then I have 3 millimoles of ammonium. So if I have large amounts of the base and the conjugate acid, That's a buffer. So we plug those numbers into the Henderson-Hasselbalch equation. So our base to acid ratio this time is what? It's not 8/3, it's actually 5/3, because we partially neutralized, we consumed some of that base to make conjugate acid in this buffer. So these two numbers are going into the Henderson-Hasselbalch equation, all right? So pH equals pKa 9.26 plus log base over acid, so this time it is 5 millimoles of ammonia over 3 millimoles of ammonium, base over acid. And so there you go. You see the pH here is a little bit more basic because there's more ammonia present rather than ammonium. Right? So see how this is a little bit different. We're not adding the base and the acid, the weak base and the weak acid straight up. We're partially neutralizing it to get a new base to acid ratio that we need for that Henderson-Hasselbalch equation. All right, we're going to do another one. Okay, this one's a tough one. One last tough one. Okay, so there's HF, there's the pKa. All right, we prepare a buffer that is 0.1 molarity HF and 0.2 molarity NaF. So first, let's take this information. What is the pH of this buffer? So it's a buffer, so we use the Henderson-Hasselbalch equation. Let's look and see what's in this buffer. We have HF and we have NaF. Can I put those numbers straight into the Henderson-Hasselbalch equation? We have HF, that is the conjugate acid. Is NaF its conjugate base? Yes, it is. So we can just put these numbers straight into the Henderson-Hasselbalch equation because it's HF and NaF. In the previous ones, we couldn't do that because it was one of the things was like a strong acid or strong base. So we can put these numbers straight into this equation. So pH equals 3.18 plus log. We can just keep these in molarities because they're in the same volume. So log base over acid is 0.2 molarity of the base over 0.1 molarity of the acid. And so we see that the pH is 3.481. Right? So there's our pH initially. All right, so let's say we add 10 milliliters of strong acid, so HCl, to this buffer. What is the new pH? So before we move on, if we start with a buffer and add acid, how should the pH change? It should become more acidic, yes. So what we're doing here when we add acid, a little bit of strong acid to a buffer, is that we're going to change the base to acid ratio, right? Because right now we have a 2-to-1 base to acid ratio. So we need to figure out how much of that strong acid reacts and changes that ratio. So we need to do a BCA table here in order to do that. But remember, when we do ice tables, we keep things in molarity. That's fine. But when we do BCA tables, what does the unit need to be for a BCA table? It has to be in moles, all right? So we need to figure out how many moles of everything we have in order to figure out what the new base to acid ratio is. So the idea here is if I'm adding HCl, which one of these things of the buffer is it going to react with? So HCl is my reactant. What is the other reactant? Is it HF or is it NaF? Not HF is an acid, so will two acids react with one another? No, so it's actually it's HCl and NaF are going to react. Acids react with bases. So I'm going to just write the reaction first and then we'll put in the values. So the reaction that's happening is we're taking NaF. I'm just going to say F minus. All right. We're taking the base. We're adding HCl to it. And so when you neutralize an acid, now let's write the full equation. So we have NaF, HCl, do our double displacement reaction. One of our products is HF, and then the other product is, what is the other product? NaCl, perfect. Right, so that's the reactions that's happening. I'm taking the base, I'm adding an acid, and look, When I neutralize this, this is how I get my conjugate acid. Now I need to put in the numbers. So let's look at all of the numbers here, and it's probably best if we work in millimoles. So 10 times 0.2 molarity HCl. How many millimoles of strong acid do I have? 2. 2 millimoles of HCl. Perfect. So I also have to do the acid and the base. So 100 milliliters times 0.1 molarity HF, there is 10 millimoles of HF present before the reaction. And then how many millimoles of the base do I have, NaF? 20. So 100 milliliters times 0.2 is 20 millimoles of NaF. These three numbers are going to go into our BCA table in the B line. All right, so I'm mixing all these things together. I want to see what happens. So I have 20 millimoles of NaF. I have 10 millimoles of HF, and then I have 2 millimoles of HCl, and I have 0 NaCl, right? So what we're looking at is just the reactants reacting. So tell me, which is my limiting reactant? HCl. So I'm going to fully consume that HCl. So if I consume the HCl, how much of the base do I consume also? -2. All right, so I consumed my reactants, but then I also do what? Produce products. So if it's -2 on the reactant side, what is it on the product side? +2 and +2. So after this partial neutralization of a buffer, I have 18 millimoles of F-. I have 0 HCl. I have 12 millimoles of HF, and I have 2 millimoles of NaCl. So this is everything that's in my water after the neutralization. Does NaCl do anything to our pH? Think about chapter 16. If you put NaCl in water, how does the pH change? It's pH neutral. So NaCl doesn't do anything. So I can literally ignore NaCl. But what about the other two things? What if I mix F- and HF? What is that? That's a buffer. Yeah, so I created this new base to acid buffer ratio, and these are the numbers that I'm going to use to calculate my pH now after that partial neutralization. See how I converted some of the base into the conjugate acid, and that is what changes the base to acid ratio. So our pH now, so just like before, we're going to take the after line, but ignore NaCl because it's pH neutral, and say, okay, pH equals 3.18 plus log. What number goes up top, 18 or 12? 18. So it's log 18 over 12. And when you do that, you get a pH of 3.356. So how did the pH change? It went down. It went down because we added acid. We took some of that base and converted it to acid. So this is definitely a harder question where, okay, we're starting with a buffer. Get those millimole amounts, add a little bit of acid or add a little bit of strong base to change that base to acid ratio within our BCA table, right? We converted some of the F- into HF in that BCA table, all right? And there it is. Okay, so that one's definitely harder. And so what did we see here? When we start, did the pH change that much? 3.4 to 3.5? No, it didn't change that much, but we added a strong acid, right? This HCl has a pH of less than 1, I think, right? So this is a really, this has a really low, a really acidic pH, but we added some of it, 10 milliliters of it, and it didn't actually change the pH of this system that much. And the reason is because that added HCl just goes into changing that base to acid ratio and not actually affecting the pH directly. And that's how buffers work. When you have a buffer system and you add a strong base or you add a strong acid, what you're doing is just doing a BCA table. You're just changing the ratio between the base and acid plugging it into the Henderson-Hasselbalch, and you see that the pH doesn't change that much when we start with a buffer. Versus if you just put acid into straight water, the pH is going to change drastically because all that H plus goes into changing the pH. So that is how buffers resist pH change. It's because adding H plus, a strong acid, or hydroxide only just changes that base to acid ratio a little bit to then just change pH a little bit from that Henderson-Hasselbalch equation. So that's how buffers work. We're going to do some titrations here and really highlight pH calculations using that Henderson-Hasselbalch equation. But again, this is the importance of buffers, that you can identify a substance being a buffer if you have large amounts of HA and A minus present at the same time. The pH is resistant to large pH changes when strong acid or base is added, because all you're doing is changing the amounts of base and acid present in that buffer. This is also due to the common ion effect, because we're just kind of disrupting this equilibrium a little bit. But a buffer is most resistant to pH change as long as the base to acid ratio is within 10. So once there's like a lot of base and not a lot of acid, if you add more base, then you kind of run out of acid, weak acid to resist pH change. That's what I wanted to say. But once you're outside this range, this like 1 to 10 ratio, then your buffer starts changing a lot. But as long as you're inside this 1 to 10 ratio, your pH won't change that much. So here's an example. This is a titration where our buffer region is right here with added strong base. So you see that we can add a lot of strong base and the pH doesn't really change. Right, that's our buffer region. But we see at the beginning of this titration, our pH changes drastically because we're outside of that optimum pH range. Or up here, right, we see, oh, you add 1 drop of sodium hydroxide and the pH changes drastically. And again, this is because now we're no longer in our buffer region outside this pH range. But right here, this is our buffered region where pH only changes minimally. And so you actually have all of the skills to calculate every single pH point on this titration curve. You just need to know when to use what equation, right? And that's the next part of these slides. So let's talk about, demo. All right, so the last thing here is buffers with high concentration are more resistant to pH change, because if there's more base and more acid, right, if these numbers in your BCA table are very, very large already, adding HCl or adding sodium hydroxide will only change these numbers a little bit, versus if these are really small numbers, your buffer is less resistant to pH changes. So let's look at a demo here where I highlight that. Okay, so let's put the goggles on. Okay, so I got some random solutions here, and we'll see how pH changes are affected. So I have some indicator in here. So these 3 solutions all have the same pH. How do I know they all have the same pH? They're all the same color. Yes, they're all the same color. So this, I think, is just straight water. All right, so is this a buffer? No, it's just water. So do you think water will be resistant to me adding HCl to it? No. So what's going to happen when I add this HCl to just plain water? It's going to become really acidic, and probably what will we observe? Color change a lot. So let's see if that happens. Okay, I'm just going to add a drop, and let's see what happens. Did that change? Yes, it did. All right, perfect. So that was just with 1 drop. So let's do the same thing. I'm going to move this one over here. I have 2 buffers. This buffer is made with concentrations of 0.1 molarity acid and base. This buffer is made with 1 molarity acid and base. So if we just think about mole amounts, which container has more moles of buffer present? This one. This is 1 molarity of each. This one's 0.1 molarity of each. So based upon what I said, which one is more resistant to pH changes? this one or this one? This one, perfect. So let's do it, and I'm gonna do it as analytically as I can. And I'm going to add 1 drop of strong acid to each of them, and we'll see how the pH changes. Okay, 1 drop, 1 drop, 1 drop, and let's mix it. Okay, so there's this one. Did that one change color? No. Did that really change color that much? Yeah, not as much as this one. So let's add a couple more drops. So let's add a squeeze this time to both and see what happens. All right. Is this one starting to change color? Yeah, this one's starting to look more like plain water. So it looks like I changed the pH to a more acidic regime. But what about this one? Is this one changing? No. So let's add another squeeze to this one, another squeeze to that one. Okay, yeah, this one's really acidic now. It could really only handle 1 squeeze of acid, but this one's not changing that much. So let's see how much acid I have to add to really get it to change. Okay, that was 4 squeezes, 5 squeezes. Is it changing? No, it's not. So I probably have to add a bunch to get it to change. So there we go, big squeeze. There we go, finally got it to change with adding a butt ton of acid to it. And that's because there's just more moles of stuff, right? In the BCA table, the before line has big numbers for this one because there's lots of moles of things. But in this one, there's still base and acid present on both sides of that BCA table, but the numbers are just smaller. So we get a more drastic change in that base to acid ratio when we add something like a strong acid or a strong base. All right, so there we go. All right, so we use the Henderson-Hasselbalch equation when you have a weak acid and its conjugate base present both at the same time. Well, what if you mix a strong acid and a strong base? Okay, so a mixture of a strong acid and a strong base is never, ever a buffer because there's nothing weak in it at all. And so this highlights the importance of a BCA table when we neutralize something, when we partially neutralize something. So let's calculate the pH of a solution when we mix these things. The skills are exactly the same, but we want to inspect what do I have in my mixture after that neutralization reaction. And that will dictate what equation I need to use. So we mix 40 milliliters of HCl and 50 milliliters of sodium hydroxide. What is the pH? So this is the strategy. We want to figure out how many moles of stuff react. So let's convert these into millimoles. All right, how many millimoles of HCl do I have? 4. 4 millimoles of HCl. And then how many millimoles of sodium hydroxide do I have? 10. Do we like millimoles or are we resistant to it? You like it? Yeah. So just keep practicing and you'll see. So millimoles of sodium hydroxide. Because I like 4 and 10. I don't like 0.004 and 0.01. I don't like those numbers, right? These numbers are easy to see. Which one is our limiting reactant, HCl or sodium hydroxide? HCl. So here we're doing a full-blown chemical reaction, a full-blown neutralization reaction. So we actually have to do a BCA table first. There's no ice table about this. There's nothing weak present when we mix HCl and sodium hydroxide. So simply I see, oh, we have 4 millimoles of HCl, 10 millimoles of sodium hydroxide. All of the HCl reacts. I also consume 4 millimoles of base, so I'm left with 6 millimoles of sodium hydroxide. Those are all of the reactants reacting, so let's look and see what products are made. So I make 4 millimoles of NaCl. This is sodium hydroxide. This is HCl. And then I have 4 millimoles of water, but who cares about that? All right. So this is what's in my container after neutralization. All of the HCl reacted, and then what's in excess? The base. The base is in excess, and that is what's going to dictate our pH. But if you notice here, okay, yeah, I have 6 millimoles of sodium hydroxide, but I also have NaCl present. How will I calculate the pH of that? Is there something I can ignore? Yeah, you can ignore the NaCl. Why can I ignore the NaCl? It's pH neutral, yeah. And so if you have a strong base and something that's pH neutral, that base is going to win. in the end anyway. So how do you calculate the strong base of that? Or sorry, how do you calculate the pH of this mixture then? Do I have to use the Henderson-Hasselbalch equation? No, the only thing that's present is a strong base. Do we remember how to calculate the pH of a strong base? How do we do it? You just get POH, yeah. But do I POH 6? No, what do I actually have to calculate first? The concentration of sodium hydroxide. So I need to figure out, okay, let's take that excess sodium hydroxide, so 6 millimoles, and now I actually have to calculate the concentration. So before we did Henderson-Hasselbalch, it was fine to keep things in millimoles because we were looking at a ratio, but if we're calculating pH of a strong acid or strong base, just like before, we need an actual concentration. So 6 millimoles, now we need to get the volume. And if we put the volume in milliliters in the denominator, the unit that comes out is a molarity. So a millimole divided by a milliliter is a molarity. So how many milliliters is this mixture? Is it 50? It is not. It is actually 90. Yes, because you mixed 40 milliliters of that, 50 milliliters of the other thing. So this is 90 milliliters total. All right, so 6 divided by 90, I think, is 0.0667 molarity hydroxide. All right, negative log that, and you get POH is equal to something. I didn't write that down. All right, so negative log 0.0667 is 1.17. This should probably have, 2 sig figs, so 2 decimals. 1.18, and so we get our pH is 12.82. All right, more hydroxide is present. This is a basic regime. All right, so this slide actually also highlights when we mix a strong acid and strong base, and right at the equivalence point. At the equivalence point is when moles of acid is equal to moles of base. So let me just erase this real quick. All right, what if I had 10 millimoles of both of those? Right, so what if I started with 10 millimoles of HCl, 10 millimoles of strong base, sodium hydroxide? What stuff is present afterwards? Just NaCl, so we would have 0 HCl, we'd have 0 sodium hydroxide because they fully react with one another, but then what do we also have? 10 millimoles of NaCl. So if that is in our beaker at the equivalence point, when moles of acid equals moles of base, and you just have NaCl present, what is the pH of this mixture? 7. So when you have a strong acid and a strong base, it's just at the equivalence point, all right? Right when the moles of the acid and added base are equal to one another, the pH is 7. But as soon as you add one more drop of base, does the pH change? Yeah, it changes drastically because now we have hydroxide to affect that POH and pH. It's just right at the equivalence point, pH is 7. And the reason is because NaCl is the only thing that's present for that moment of time. So we see right here at the equivalence point in both of these graphs, it's like you start with an acid, add a strong base, or start with a base, add a strong acid. At the equivalence point, those both are 7, right? All right, so in this example, we still used a BCA table, but the strategy is just a little bit different because in the after line, okay, I'll erase all this stuff. In the after line, we don't have any weak systems, so it's not necessary to use the Henderson-Hasselbalch. We just look and see, okay, what is left over? That is what dictates our pH, right? Okay. Okay, let's practice. Remember, there are 2 ways to make a buffer. I like this game. So I'm going to give you a bunch of combinations of things, and you tell me, can these things make a buffer? Remember, what do you need to make a buffer? You need an acid, so like HA, and its conjugate base. Those 2 things have to be present in the solution, but there's 2 ways to get that. Either add them directly or via partial neutralization. So you can have an acid and its conjugate base, or you can have a base and its conjugate acid. All right, But remember, we can make conjugate acid by adding a strong acid to a base. So let's go through all of these and you tell me, can you make a buffer out of these things? HF and sodium hydroxide. Yes, because that sodium hydroxide will neutralize some of that HF to make F minus. Yes, that is a buffer. Which buffer is that, the first type or the second type? The second type. So do you have to use a BCA table for that one? Yes, you do. The next one, HF and HCl. No. Ask yourself, HF is a what? A weak acid. HCl is a what? It's a strong acid. So 2 acids? No, that's never going to be a buffer. Right? That's 2 acids. All right. HF and KF, is that a buffer? It is a buffer because HF is your acid, F minus, that's the base. All right. What kind of buffer is that, the first one or the second one? That's the first one. So do you need to do a BCA table for that? Nope, just get millimole amounts of both, plug it in to Henderson-Hasselbalch. All right, ammonia and nitric acid. Is that a buffer? Ammonia, is that a base? That's a base, that's a weak base. What about nitric acid? Strong acid. Strong acids react with weak bases to make NH4+. Yeah, so this is a buffer. Which kind of buffer is it, the first one or the second one? The second one, the one where you partially neutralize it to make your buffer. So you have to BCA table that one. So that one needs a BCA table, the first one needs a BCA table, then you Henderson-Hasselbalch, right? The third one we did, you just Henderson-Hasselbalch straight up. Next one. Oh, I have the same one twice. Okay, perfect. Ammonia and ammonium bromide. Is that a buffer? Yes, it is. Do you have to BCA table? Nope, you put that straight into the Henderson-Hasselbalch. So that's number 1. Benzoic acid and sodium benzoate. Is that a buffer? Yes, it is. Do you have to BCA table? You do not, because benzoic acid, that's your, so I'll just call that HA. HA. Sodium benzoate, that's NaA. So there's HA and A minus, you just Henderson-Hasselbalch straight up. All right, benzoic acid and KOH. Is that a buffer? Are you sure? Benzoic acid is HA, it's a weak acid. KOH is a strong base. Strong bases, do those react with weak acids? They do, to make A minus. Yeah, this is a buffer. Do I have to BCA table here? You do. You do have to BCA table because that KOH, that strong base, is going to react with that weak acid to make sodium benzoate or potassium benzoate in that solution. So this is the second type of buffer. This one is actually no different than this first one. HF and sodium hydroxide. There's a weak acid. There's a strong base. Benzoic acid is a weak acid. KOH is a strong base. It's no different. All right, benzoic acid and HCl. No, why is it not a buffer? Those are 2 acids, yes, so no. All right, keep going. All right, NaCN and HCN. Is that a buffer? It is. HCN, there is HA. NaCN, there is A minus. So that is a buffer. Do you have to BCA table? Nope, that one you plug straight into Henderson-Hasselbalch. All right, NaOH and HCN. Is that a buffer? Yes, it is, because HCN that's HA, that's your weak acid. Sodium hydroxide is a strong base, so you'll neutralize some of that HA to become A minus. That is a buffer. Here you do have to BCA table, then Henderson-Hasselbalch, because you partially neutralize first. All right, HCl and sodium hydroxide, is that a buffer? Are you sure? Yes, it's an acid and a base, but it's a strong acid, strong base. So this is not a buffer. But you can still calculate the pH of that, right? You just BCA table first and go straight to calculate your pH. So you could BCA table and then you just calculate pH directly. But no Henderson-Hasselbalch because it's not a buffer. All right, NaCl and HCl. Is that a buffer? Yes? No, it's not. Why? strong acid, and a neutral salt. This is actually just acidic, so this is not a buffer. Yes, this is just, you calculate the pH using HCl because NaCl is pH 7. All right. Okay, next one, NaOH and acetic acid. Is that a buffer? Yes, it is. It's a type 2 buffer where you have to BCA table first and then Henderson-Hasselbalch. Okay, keep going. This thing and this thing, is that a buffer? It is a buffer. This first thing looks like ammonia. This second thing looks like ammonium chloride. So this is a buffer. This is my base, and here is its conjugate acid. So do I have to BCA table this? No, you just Henderson-Hasselbalch those mole amounts straight into it. Okay, next one. This thing that looks like ammonia and sodium hydroxide. No, it is not a buffer because what two things are in solution? Two bases, so that is not a buffer. How would you calculate the pH of that, you think? NaOH, because it's the stronger one. Yeah, the ammonia-looking thing contributes some hydroxide, but just a really small amount. So sodium hydroxide is going to be the thing that dictates that pH. All right, last one. Three more. The ammonia-looking thing and HCl, is that a buffer? Yes, it is, because we got a base, we got a strong acid, so that's how you get the weak acid for your base to acid ratio for your Henderson-Hasselbalch equation. So in this one, you have to BCA table first, then Henderson-Hasselbalch. All right, nitric acid and KOH. Is that a buffer? Nope. Why? Yeah, two strong things. Yeah. So if you wanted the pH, you just BCA table, put it straight, and take the excess thing to calculate pH. So I'll just write BCA, and then you just calculate pH directly. All right, last one. These two things. Is that a buffer? Squint your eyes. What does that look like? Ammonia. Squint your eyes. What does that look like? Ammonia with an extra proton on it, and that is a conjugate acid. So there is our base, there is our acid, so this is a buffer. All right, but in this one, you just plug it straight into the Henderson-Hasselbalch because you already have your base and acid present. All right, so, I mean, this chapter 17, there's a lot of things. Identifying weak acid, weak base, is the thing I'm mixing together, does it make a buffer? On top of it, different types of calculations. I have another one of these slides coming up where we determine, okay, when we mix these things, do we make a buffer? These things definitely are tricky, but, practice makes perfect. All right, so, So we will move on to acid-base titrations. So here's the thing. You know how to calculate every single point on this titration curve. Every single one. We already did examples of all of them. The difference is during a titration, it's not obvious what is in your beaker at each point of your titration, so we need to figure out what is the important substance in my beaker for all of these points in a titration curve. We know every single calculation already, all right? So let's go and think about what's in my beaker at all of these different points. That's how I calculate, the pH, all right? And you will do 2 of these labs. You'll do strong acid, strong base in one of your labs, and you can calculate pH at every single point. And then you'll do a weak acid system at a strong base. You can calculate the pH at every single point. But you'll also measure it, but you can calculate it. So let's move into it. Okay, so let's let the titrations begin. So the important thing here is ask yourself, what's in your flask? If you start with a weak acid in your flask and you put in a pH probe, that pH is dictated by just that weak acid. Or if you just have a weak base present, then your pH is dictated by that weak base. If you have both the weak acid and its conjugate, that's a buffer. So the pH is dictated by the buffer. So we need to think about what is in my flask. So let's pretend we're doing a titration. You put an acid in that beaker, HA. and you start adding sodium hydroxide, right? So we're doing this reaction. So we might like start with like 10 millimoles of HA, I'm just making up a number, and then we're adding small increments of sodium hydroxide. So we need to ask ourselves, what is in my beaker at every single point here? So at the beginning of my titration, right here. So this is before I add any base at all. If I put a pH probe into here, the only thing in my flask is HA. That's it. I haven't added any base. Do you know how to calculate the pH of something that's just a weak acid? Yeah, that was from chapter 16, right? You just do x squared over initial concentration equals Ka. That's your pH. So as long as you know the concentration of your weak acid, you can calculate the pH because HA is the only thing that is in there. Okay, so let's pretend we add a little bit of sodium hydroxide, so 2 milliliters, right? 2 milliliters. So we consume some of our acid. We make some of its conjugate base. What is that? That's a buffer. Yeah, so you actually have HA and A minus present in your beaker. How do you calculate the pH of that? Henderson-Hasselbalch, right? So that is this flat region of our titration curve. Actually, before we move on, where is the equivalence point on this titration curve? At what volume? 10. So right here, that is our equivalence point. So leading up to that equivalence point is our buffer region. So 2 milliliters, 8 milliliters, both of those regions, you actually have a buffer because you have both HA and A minus present at the same time, right, at the same time, because you're partially neutralizing it. So let's say at 10 milliliters of base added, you know, we started with 10 milliliters of HA. Now we have 10 milliliters of sodium hydroxide. Those two things fully react. So hopefully in your head, do the BCA table in your head with those amounts. What's present in your beaker at the equivalence point once you've added the same mole amounts of sodium hydroxide? You actually have converted everything into NaA. What is NaA? It's not a weak acid, it's actually a weak base. Do you know how to calculate the pH of a weak base? Yeah, it is x squared over initial concentration, but it has to be equal to Kb. That's chapter 16, right? Where we get Kb from Kw over Ka, right? So this is your equivalence point. Equivalence point where you've converted all of the HA has now been converted to NaA. All right, what if we add a little bit of extra base? What's in your beaker now? You still have NaA present, but now you have excess sodium hydroxide. And so if you have those two things in your beaker at the same time, which one dictates your pH? The weak base or the strong base? The strong base. So here, we're going to just use the excess sodium hydroxide to calculate pOH and then calculate pH. And that's it. You actually know how to do every single one of those calculations already. We just have to decide, given the information in the titration, well, where are we on this titration curve? Which calculation do I do? All right, so let's do it. Okay, this first one. So this is before you begin your titration. You put 10 milliliters of 0.1 molarity acetic acid in a flask. What is the pH? So you got to ask yourself, what's in your flask? So we're right here on the titration curve. This is before we even start. All right, so let's call acetic acid HA. So the only thing we have in our flask is HA. That's a weak acid. If it's a weak acid, we should probably use Ka. This is from chapter 16. Right, where, okay, let's write the Ka expression for HA. We do our ICE table, where all of that's in molarity. We put 0.1 molarity HA into the water. This reaction has to go which way? Forward. So it's minus X plus X plus X. So at equilibrium, we have 0.1 minus X X amount of that, X amount of that. So at equilibrium, Ka, which I give you is 1.8 times 10 to the negative 5, equals x squared over 0.1 minus x. Can you solve that? Yeah, but do you want to do the quadratic? No. So what are we going to do? Get rid of that minus x. Now it's quite easy to solve. And so we solve for x. Did I write that down? No, I didn't. Of course not. Of course not. Nope, didn't write it down. Okay, so 1.8 e negative 5 times 0.1, take the square root of that. So I get x is 0.00134 molarity, but it's the molarity of what? H plus, because we used Ka. And so when you negative log that, you get a pH is 2.87. HA is the only thing present. That's the only thing you added into the solution, into your Erlenmeyer flask. So we just do the x squared over initial concentration. Okay, that's a chapter 16. This is before we begin the titration. There's only one thing present. It's no different from chapter 16. Okay, now let's add a little bit of base. So we're going to move forward in this titration curve. But before we even answer it, if we add a little bit of base, how should the pH change? It should go up. So make sure after this calculation our pH goes up, because if it goes down, you did something wrong. Yes, okay. So we still have that acetic acid, but now we're adding 2 milliliters of sodium hydroxide. All right, so we're taking a weak acid and we're adding a strong base. Those two things react with one another. So we have to neutralize them first to figure out, after that neutralization, what is in my beaker. So we have to BCA table first. This is a type 2 buffer, all right, where we're creating a buffer, but after a neutralization. So we need to get millimole amounts now, because before we didn't have to get millimole amounts. We just plugged it into the ice table. But now, because a neutralization is happening, we need to get millimole amounts. So how many millimoles of acetic acid are here? Is that 1? 1 millimole of HA. That's my weak acid. How many millimoles of base do I have? 0.2 millimoles of sodium hydroxide. These two values go into my BCA table. So BCA, 1 millimole of HA, 0.2 millimoles of hydroxide. None of that. So when these things react, which one's my limiting reactant? Hydroxide or weak acid? Hydroxide, so it's minus 0.2, but it's also plus 0.2. And again, I don't care about water. So after this neutralization, I completely consume my hydroxide, but now I am left with 0.8 millimoles of HA and 0.2 millimoles of A minus. Is that a buffer? That is a buffer, but we had to get the correct base to acid ratio by reacting that sodium hydroxide first. So since both of these things are in the solution, yes, I just do the ice table, but we can just use the Henderson-Hasselbalch equation now, right? Because we have large amounts of the acid and its conjugate base, all right? So here, you know, you can do the ice table, but essentially I'm just going to use the Henderson-Hasselbalch equation because both those things are present. So pH equals, I give you the pKa, 4.74 for acetic acid, plus log, what number goes on top? 0.2. 0.2 on top, 0.8 on the bottom, and we get that the pH is 4.14. Did our pH go up when we added base? It did. Right, we started at, when it was just the weak acid, 2.87. Now we added a little bit of base. It went up, became more basic. Now it's a pH of 4. Okay, let's add a little bit more base. Okay, all right, so we first added 2 milliliters of base. Now let's bring that total volume added to 5 milliliters. Let's see what happens. So, well, first, let me ask you, have we reached the equivalence point yet? Nope, we haven't. Where is the equivalence point? Because that'll help you in your calculation. At what volume of sodium hydroxide is our equivalence point based upon these two numbers? 10. So we are still well before the equivalence point. So this is still a buffer. But let's actually calculate it. We actually need those millimole amounts again. Oh no, my pen died again. So the millimole amounts, we're not adding acid at all. There's still 1 millimole of HA present. All right, this is still 1 millimole. But now we have 0.5 millimoles of sodium hydroxide. So when we BCA table this, the only number that changes is the hydroxide. So this is 0.5. The reaction still moves forward, completely consuming that hydroxide. But we add half a millimole of A minus, and that's the important part because that's how we make a buffer, the type 2 buffer, where we start with a weak acid, add a strong base to make A minus in that solution. So we see after this neutralization, we are left with 0.5 millimoles of HA, 0 hydroxide, and 0.5 millimoles of A minus. Is that a buffer if both those things are in your beaker? Yes, it is. So how do we calculate the pH of that then? Henderson-Hasselbalch. So just put that as your base to acid ratio. So go ahead and plug that into pH. So pH equals pKa, 4.74, plus log, what number goes on top? Or I guess they're the same, but it's 0.5 base, 0.5 acid. So you see that, oh, that equals 0. And so we see here the pH equals the pKa, 4.74. Perfect. Right? And so again, pH equals pKa when the moles, the amount of acid and its conjugate base, are present in equal amounts. Okay, so let's keep going. Scenario 3. What are we adding together? So note here, you would do the same exact calculation for 6 milliliters, 7 milliliters of sodium hydroxide, 8 milliliters, 9 milliliters, same calculation. You start with the BCA table first, put that new ratio in the Henderson-Hasselbalch equation. But now in scenario 3, we're adding 10 milliliters of acetic acid and 10 milliliters of sodium hydroxide. Is this a buffer? It is not, because now we have completely neutralized our acetic acid. All right, so let's just do a BCA table to see what is in our beaker when we add these two things. So there is 1 millimole of HA present. There is 1 millimole of sodium hydroxide. So when we mix these two things together, BCA, technically both of them are a limiting reactant. Right? So in the change line, it's -1, but it's also +1 for water too. So after this neutralization, I have 0 HA, I have 0 sodium hydroxide, but I have 1 millimole of A minus. All of those things are in my beaker. A minus is a what? It's a weak base. Do you know how to calculate the pH of a weak base? Yes, that's chapter 16. All right, so if this is a weak base, we use what equation to solve for it? KB, yeah, we do x squared over initial concentration equals KB in this case. But remember, initial concentration, 1 millimole is not a concentration. So now we actually do have to calculate what the concentration of A minus is. So we do not use Ka. We're using the Kb expression because A minus is a base. So A minus concentration is 1 millimole over, what's the total volume? 20. So 20 milliliters, so we get that the concentration is 0.05 molarity A minus. So to solve for the pH, it is x squared over 0.05 molarity equals Kb. How do I get Kb? Kw over Ka, so 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5. All right, and then you solve for x. I didn't do this. But x equals what in this case? Equals concentration of what? OH minus concentration, yes. So once you get that value, you can calculate POH, and then you get pH. And we see, oh yeah, we keep adding base, it gets more basic, right? This is a chapter 16 question, but you just need to recognize that A minus is the only thing in my beaker, right? And so the last one, which we won't get to, is the last scenario, you add too much sodium hydroxide, how do you calculate the pH? So we'll pick up there on, next week, yes.